Hello guys, and welcome to another video on the Energy System Analysis Python course. My name is Anas Abuzayed, and in today's video we will talk about data manipulation, data preparation, and how to handle data generally inside pandas. So in today's lecture we will use two data frames that I share with you, one Excel file, one CSV file. So we will try to read them inside Python, see what exactly they are about, and then take it from there slowly. So let's start by importing our libraries. So import pandas and NumPy. So the first data frame we call is line description or lines description. This is an Excel file. So let's see how we can read it using Python. So let's say I'll just use it, or let's say the pd.read Excel, and then you put the Excel file name. So lines description dot. So the first error you will see, because in my case, my current repository or my current working directory is the desktop. So it says that there is no such file. So in order to solve this, I created a folder in my desktop called Energy System Analysis, and I put all of the data in there. So how can I change the working directory, this one here, into the new one that I want, which is Energy System Analysis? So it's a folder inside desktop. In Spider, it's quite easy. So Energy System Analysis, that's my folder name. Now, if I read it, it's done. How can you do it without manually doing it from here is by another library called OS. So let's just import it. So import OS. And then from OS, there is different functions that we can use to deal with path. So one of them is OS get current working directory, so CWD. This would give you the current working directory. So now it's changed. You can see it already. And one of them is OS dot change dir. So change directory. For example, here, if you copy this one, let's say back to desktop and execute it, you'll see now it's changed. And if you put energy system analysis next to it, so energy system analysis. So if you see here and now executed, now it's done. So we already read our file. Let's see what's exactly in there. So this is a description of the other data frame that has data on the transmission, the high voltage transmission lines in Germany. So let's read the other one and see what's exactly in there. So let's say df equals pd.read. The other one is a CSV file. So CSV, and then the name of the file lines underscore de.csv. So if we say df, we cannot see all of the 17 columns. So we can just open it from here easily inside Spider. That's mainly the main reason why I use Spider, not other IDEs, because I can somehow open data, access it, see it visually, like I'm using a normal Excel or Microsoft Excel software. So if we go back to our previous data, which is the description data, you can see that LID, it's basically the line ID. VID1 is from node to node. What's the voltage? How many cables, wires? What's the frequency of the line? The name of the line, the operator of the line, the reference number, the length in meters, and then the electrical characteristics. So R, X, C, and I. So thermal I. And then there is from relation here, it says NAN, so it's not known. And we have the SRID, so the Spatial Reference System ID, or the decimal degrees, so basically the longitude and the latitude. You can see them here inside Python or inside Spider. And then we want to start using different functions just to explore what exactly is this data frame. So let's start from the beginning. So in order to see the indexes, Now the index is a range from 0 to the last number. So it's 836 lines. So it will start from 0 to 835. In case I want the line ID to be the index. So instead of it starting from 0 and so on, so I want the line ID to be my index. Another argument here in read CSV would be index column, and this would be to 0. So the first column here, so if you say df columns, my first column is line ID, and if I put 0 here, then df.index, it will be not a range as we did previously, so but the line ID. Let's say instead of 0, we put voltage just to try it. So 0, 1, 2, 3. Now if you run it again, so you will see the voltages, the line voltages. Of course, we don't want it, so let's say 0. Now we have our index. So what are the functions that you can, let's say, use on a data frame? One very useful function is unique. So let's say df dot voltage. So we want to know how many voltage levels are there in our data frame. So how to use the column or how to call the column either this way or that way. That's clear from the previous video. So df dot voltage. Now you see 836. So there's no way that you access each one of them just to see which or what are the unique values. So dot unique gives you the exact unique value. So all of the 836 values are basically one of those 5 values. So 220, 380, 400, 450, and 300 kVs. Another function we said previously about the NaN, so not a number. Say we want to check if each of the columns has an NaN value or not a number, a numerical value. In our case, it's a data frame, so there might be some missing values. So there are different ways how to check it. One of them is df.count. So our data frame.count. Then this would give you, so we know from the length of our data frame, it's 836. So here df.count will give you how many exactly their values are, how many not NaN values. So for example, for voltages, ID1, ID2, it's perfect. For cables, it's not. For wires, it's not. Frequency, name, and so on. So for length, it's okay. This one we don't need. And for the SRID, it's okay. But the electric characteristic, the lengths, the reference operators, and so on, plus the cables, there is NaNs. So our goal in this video is to try to handle this or those NaNs and change them or learn ways how to change them. So different ways how to change them. So this is one way of knowing how many NaNs is there. Another one is if we say df.sna. So if you do this one, it basically returns a false and true every time. So a true every time there's an NaN, and a false every time there's not. But here it's somehow very difficult to know. So if you remember from the previous lectures, if we want to know if there is any true in there, so true means that it's NaN. So if we say dot any, then it will return true for each column that there is not a numerical value. So if we execute it now, then we see, okay, cables, wires, frequency, and so on, plus the electrical properties, all of them will have NaNs. So the easiest way, of course, is to drop all of them. So if we say df.drop NA, then basically it will reduce it from 800 to 156. Here, note that we did not say in place equals true. We know that in place replaces it. So let's say we execute it now, our df has 156. You can also see it here. So let's read it again. We don't want to do that. So if we want to check if we drop NAs or drop all of the NANs, so any row that has NANs, just drop all of it. Will this make any sense? So let's check, for example, the links. So we said df dot We just copy the column name. So length square meter. So that's the total length for the transmission lines from this data set. So if we sum all of it, that's roughly 31,000. So over 1,000, that's 31,000 kilometers. So if we drop it, let's say A equals the dropped one, and then A dot length dot sum. So now we have 8,000. So let's say 1,000. That's 8,020 kilometers. So nearly we lost 75% of the transmission lines. So in case we want to use this data frame to build our model in this course or even in real life in your work, if you lose 75% of your data, that's not a very good job. So there might be another way of doing that instead of just dropping all of the NANs. It makes your life much easier. So now all of our data frame, let's say if we drop it, this one, there's no missing values in it. But we nearly lost 700 lines so from 836 to 156, nearly 700 lines that we lost them and lost their data alongside. With that being said, let's try ways how can we manipulate the data. So first, let's put the columns. So we say, let's say this one here, the columns that has NANs. Let's start with cables, wires, so frequency, name, operator, and then the electrical properties. So before that, there is different columns here that we might not need. So for example, we might not need the name of that line. So we can drop it. So if we say df.drop and then the name of this one, in this case, it's name. Let's drop frequency, just for instance. So it says that it's not found in Access. Why? Because it's a column and we said the default of Access is 0. So we have to define it as 1. Now, of course, it's not executed because we did not say in place. And we know by a fact, for example, that frequency in all of Europe is 50. It's only in North and South America, and I think some countries in Asia, Japan, Saudi Arabia, North and South Korea, those deal with 60 hertz systems. But in case of Europe, it's all 50 hertz synchronized. So if we drop this one, there's not really much of information that we will lose here. So if we drop it now, it's okay. So before we drop other functions, let's say I want to drop the name of the line, the operator, the reference, and this one from relation. I'm not really interested in those. I just want to give a refreshment on the grouping, say the grouping of data sets or data frames. So if we say df dot operator, this would give me the different operators that own or let's say operate this line. So if I say dot unique, this would give me the unique operators from this dataset. So Tenet, of course, 50 hertz, Stromnetz Berlin, the Czech power system operator, there's the Polish one from Poland, there's RTE from Electricité de France, what else? There's RVE and so on, ENBW in Baden-Württemberg. So let's say I want to know how many lines are operated, for example, by Tenet or by 50 hertz. How can we do that? Is one way would be to only select the ones, let's say by 50 hertz. So what's 50 hertz? This one. So df.operator equals 50 hertz. This would give me a true and false. And then if I say like this, then it would give me only the lines, the 112 lines out of the 836 that are operated by 50 hertz. So let's say I say what's the length, summation of it. So 6,600 kilometers. The other way that I can do is by group by. So group by, and then I say operator. So if I say summation, and then I'm only interested in the length. So this would give me how many lines. Let's just do it a bit more friendly in kilometers. So 1E3 is 1000. So this would give me, for example, 50 hertz has this one, and then again 50 hertz transmission. So they are the same entities, I think, just different ways of reporting it. Also, there is 50 hertz with small h. So all of those belong to 50 hertz. Of course, because it's a case sensitive. So in this case, we need to maybe do it somehow manually. If we want to say all of the lines that there is 50 hertz in there, because I think there's also this one with the power system operator from Poland. So this also needs to be taken into consideration, this one as well. With that being said, we can basically group it and see, or let's say have a bigger look on all of the operators, how many of them or how much each of them operates or has length of lines. So again, with that being said, I'm not really interested in the operators. Same thing goes, I think, for the name, the reference. We already dropped the frequency. So let's try to drop them again. So we said we want to drop those ones here. So name, operator, and reference, and this one. So either I can do the same thing that I did here 4 times, or I can just say as a list. So if I copy it here, and then I drop them, now my data frame has 11 columns that I want to work on. So from two voltage, cables, wires, length, and then the electrical properties, and then finally the GIS information. So let's start with the voltage. Is there any NANs in the voltage? So if I say df.voltage dot SNA, and then either I say any, it's false, so there is nothing, or I just say the same one here with sum. Because false is 0, so the summation of 836 zeros is basically 0. So both are valid ways of checking if there's any N. What are the unique values of the voltage or of the voltages? That's 220, 380, 400, 450, and 300. Let's say I want to change this 400 and this 300 into 380. So I want to replace them. How can I do that? Is by df to replace, and then I put the number that I want to replace. So let's say 300, and then I replace it by 380, and then in place, of course. So if I run this, then again, if we check, now we don't have the 300 kV, and it's all replaced by 380. Let's do the same for the 400 and 450, because normally I think in German it's only 220 and 380 kVs. So again, either we do them twice, one for the 380. So let's just put 80, sorry, not the 380, the 400, and one for the 450. Or we can do it in a better way by saying, okay, replace those by 380. Now, of course it works, but I have one issue of this, because let's say our data frame contains, so here it contains 11 columns. Let's say the 380 or the 400 that we change, or the 450 for 150 kVs, or the 300, the 400, let's say they exist in other lines or in other columns. In our case, it's not, because it's only voltage here. So those are linked. I think the maximum of them is maybe so 200 here. But in case this 400,000 that we replaced, because we said df to replace, so over the whole data frame, wherever you see 400,000 anywhere in the data frame. But our intention was only to replace the voltage. So in this case, we say, basically, we specify that only in this column, if you find 400 or 450, replace it by 380. So I think for the voltage, since there is not much NANs, we will not talk further with it. So let's move to the cables. So df.cables. Now we want to see how many unique values are there. So we have 3, 6, 1, 9, and 12. So one way would be, let's say we replace all of the NANs. So let's select all of the NANs first. As an A, we return true and false. So if we say the cables with this one, this would give us exactly where it's NAN in this case. And if we see the length of those, that's 24 missing values. So let's say we replace it by the average of the cables. So what's the average of the cables? Because normally you will see that, okay, you'll see that a lot in the literature. If there is a missing value or missing values, replace them by the average, then you're good to go. So in this case, it's 3.278 cables, which makes no sense because either you can have 3 or 4 cables, or in our case, since it's a bit sensitive, so 3, 6, 1, 9, or 12. So it depends on the industry itself. Another one would say, okay, let's do it with the median. So the median in this case is 3. This is also valid. So the median is a valid statistical method, and you can do it, or maybe the maximum or the minimum. But I want to see how many values occur in this df.cables, or how many values, let's say, what's the frequency of those? And then I would make a better judgment, which number should I replace? So here we say equals, and then we put a number, let's say 3, 4, whatever. But I want to make a better judgment on this one. So let's just keep this one here empty and move it to the end, so that when we decide based on, let's say, fact-based check of our data. So if we say df.cables and then value counts, this would give us the frequency of those values. So we see that, for example, 3 happened 740 times in our data. So it would be very sensible to replace our NaN values by 3. So should I just put 3 here? It would work, of course, but let's just do it a bit more automated so that we know a bit more in Python. So how can I select this one here? I know that it has the maximum frequency. So how can I select the index of that has the maximum number? So IDX max would give me this one. So instead of just putting 3, which is totally fine in this case, but let's say you got a bigger data frame where this number was changed and now it's 6 instead of 3, then you would need to change it again. So now let's check this one. So it's 0. But here it says only a warning that we're setting a copy. So this warning in future might give you some issues. So let's try to learn another way how to access this data instead of this one, because it says here that a value is trying to set on a copy of a slice. So we took only a part of it, so not the whole data frame. So if you remember previously, it was only 24 out of 800. So it might give you warnings in the future, but it's totally fine. Now we see it here. If you say df.count, you'll see cables are now fine. And if you say df.sna, and then any, then you see that now cables does not have any ends. So let's move to wires. So same thing for wires. Let's do unique first. So let's just put here. So we have 2, 4, 3, and one wire, of course, with an AN. So there is different ways how to change it, as we did before. So let's try it first with the max, the mean, of course, makes no sense in this case, the median, and we can even do the value counts. So here, for example, you see that 4 and 2 are relatively close. So 267 and 248 happened, where 80 and 70 for 1 and 3. So, of course, there's no absolute truth here. So you can do whatever you want with with your own data. You just need to justify it in a scientific way, in a way that makes sense for people to read or for people to agree with. But when you have, let's say, or when you know a bit of background on this data, you might have a better understanding of it. So, for example, we know that wires and the cables are somehow depending on the voltage levels. So we know that we have now two voltage levels here because we replaced them, so 220 and 380. Now, if we want to know the wires when the voltage was 220, how can we do that? So let's do it step by step. So VF dot voltage equals 220. And now we select the whole data frame. So we can say either the wires here or wires here. So both are the same, just like do it here. Now we have 400 elements where the voltage was 220 out of the 800. Now if I say dot unique and dot value counts, I would see that for 220, it makes more sense that I put 2 for the NANs instead of 4 or instead of the median. Now, if you do it for the 380, you would see that 4 makes more sense. And even let's say that we did before, so we had previously 4 and 2 to be the best two candidates for our replacement. In case of 380, 2 was the third favorite, so the third place, not really the first one or the second one. Same thing here for 4. So 4 cables, we had 2 that happened 216 times and 1 that happened 78 times. So when you understand the background of your own data, or let's say you have a background how things work in reality, you can have a better judgment on the data manipulation and the data correction, let's say the data preparation of your data sets. So we did that previously here. That said, it had kind of a warning. So let's do it twice, one for the 220 and one for the 380. So for the 220, we want the 2 here, which is the IDX max. So this is the value that would be on the right-hand side. Now let's choose the value on the left-hand side. So the wires when the voltage is 220. So df dot wires and then df dot voltage equals. So now we want only the NANs. So we can do it in two ways, either by saying, okay, dot replace np dot none. Let's call this number the W20, just to assign it. So W20 in this case would be 2. Assign it, so replace this one by W20 and then in place equals true. Now if you run this will give you totally correct values. So now if you say it again, what's the unique values? You'll not see any, ideally not any NAN. But the issue here is that sometimes in place does not execute. That's very confusing. It's been depreciated in different versions of pandas. So in older versions, mostly it will work, but I assume most of you will have the newer versions of pandas. So we can either do it like we did here, or we can maybe make a bit of conditional selection by saying, okay, we want wires when it's NaN. So here, if we execute it again and now check, it's still there is NaNs. So instead of using in place, what we can use is either saying, okay, this is the new one, so this is not in place. So either saying, okay, the old one equals this one. So it's, again, it's slice or a copy, or we can use dot lock. So the conditional selection by saying, okay, we have two conditions. One is the voltage equals 220, and the other condition is that we need it to be as an A. So this case, it's already done. It's for the 380 because we already executed it. So for the 380, we have 82 rows where it has this problem. So for the value counts for the 380 was 49 times 4, and then 69 with 3, 32 with 2, so two wires, and 4 times with 1 wire. And of course, we say W38. So this one here can even say X, it doesn't matter. So W38 is 4. Now we said we did have a selection, so a conditional selection. The first condition here is that the voltage is 380, and the second condition is that the wires is NA. So somehow it's the same as this one here. Here we did replace NA, NaN. Previously, we did it directly for the whole thing. Now we do it a bit more complicated by saying, okay, we want only those. Now here it's a data frame, so dot wires, or since we're using log, so we know that all of this is on the axis 0. So the rows, now we say wires here. So those are the 82. And this would equal W38, which is 4. So now if we check df dot wires when df dot voltage equals 380 dot unique, and if we do value counts, previously it was 249, but we added 82 on it with the new 4. So now it's 331. So as I said before, you can do whatever you want. I'm just showing you different ways how to do it. So let's check now our data frame. So now we're done with all of those. We still have the last 4, which is the electrical properties. So let's do that. Now, if we say this one, and click, so we have the length of them instead of counting. We have 13 ones, or 13 different values, except for the NaN. And if we do it also for the X, in 13, and ideally we can, let's say, just say, okay, replace it by the average. Let's say if we say what's the average of this one, it's 0.06. So if you compare it to those, somehow it's okay. But we know that if you know the background of behind this data or the background behind transmission line calculations, you know that there is standards from manufacturers that they have this standard with this R ohm per kilometer, or this X ohm per kilometer, or this nanofarads, or this capacitor, or shunt capacity, or this thermal current, or maximum thermal current. So somehow it's standardized. So let's see, for example, what are the values of X and C and I when R, for example, is 0.08. So if we say we want BF dot R ohm kilometer equals this one, that's our conditional selection. So there's 211 one or ones, and we want this column. Now, if we want to see the unique value of it, we'll see that it's only one. So somehow it triggers that our theory can be basically correct. Let's do it for the C and the I. So I just need to copy the names. So for the C, and again, so when R equals 0.08, we had only one value of X, 0.32, only one value of C, which is 11.5 nanofarad, and only one value of I, which is 1.3 kiloampere. With that being said, this basically indicates that there is a set of values. So let's check this one when the voltage is 220. So we have now two conditions. One is that R is 0.08 equal to 20. And then I want to have the unique values of R, of the resistance. So now we have only 1, 2, 3, 4, and 5. Where when we did it previously on all the voltage levels, we had more. So this indicates that you might be able to create a standard type out of this data frame for your own use, either in this data frame or in other projects, that you can say, okay, based on this data frame, we found that over this voltage level, normally it's one of those values that you will find for R. And if you find it for 0.08, you will see that it was 0.32 ohms as X, so as reactance, 11.5 nanofarads, and 1.3 kilo ohms. So let's try to create this standard type. So I want to iterate over this data frame or over the unique values of X or of R. So I want to say for R and the unique values. So I want to iterate over those. And just for the case that it will not, so if I just say print R, it will print the NaN. So I want to skip the NaN, but not drop it completely, because we saw that if we drop it, we will lose data from it. So I want the data frame without the NaNs. So now it's 662. Previously, if you remember, it was roughly 100. Now we have, if we drop all of the NaNs, we lose roughly 200 values instead of 800 instead of 700 values before we did the cables and the wires. But still 200 lines is too much. So now if I iterate over this one, I have the actual values. So in each one, I want to know what is X, C, and I. So I'll just copy the previous code that we did before. So each time R is changing, and I want to know how much X equals, or how much does X equal to, or C or I. So in this one, I'll say X equals, C equals, and I equals. And let's just print R, X, C, and I. Let's run this for loop. So now we see that our theory is correct. Whenever R is 0.08, we only had this set of combinations. And because here we said the unique. So if it was more than one component, we will see that it's 0.32 and then 0. Let's say 0.75 or whatever. So it's only unique value. So for example, let's say when R equals 0.02, then X equals 0.08, C equals 46, and I equals 5.2. So what I want to do is I want to create a standard data frame where I enter how many types or how many combinations, so all of these combinations, but as a standard data frame. I might use it later on. Maybe we can use it. You can even write a small report on it that based on this data frame, you found these values that are reported in literature, so others can use it, or you can use it to your own. So I want to create maybe STD standard, a data frame where it's empty, so 0. My index, I want it to be the length of those, so just the numerical one. So let's say how many are those? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3. So I can either just say 13, so index equals range 13, or range len. We try to be as much automated as possible, so that our code will not give us error if the data changes. So range len, this one. So this one here is the 13 values, and then the range of them, so index, not nd. And then columns, I want to have R, X, C, and I. So now if we have an empty data frame that we want to say iterate over those, and each time enter the value here in our data frame so that it's more, let's say, a bit more clean than what we have here. So let's do it. The first thing that we need to do is that how can we access this data frame? So let's say we want the value of X at index 4. So std dot iloc, and then, or even loc in this case, it will not make any difference because the index 0 and the name of it is 0. So 0 and X, or 4 and X, or even 13 and X. Plus, in this case, 12 and X. So the last one. So that's the first thing. And now here I want to say, okay, std.log R equals R. I need a number that is changing here. How can we do that? Because that's here in the number. Either I say I change completely the whole data frame, the whole for loop in to range len, then it would be indexes, or the easiest way is to use enumerate. And then here we add another variable. So if I say idx and r, it will basically give me the index, the first 0, 1, 2 till 12. And here I'll just say idx. So this one, now we see our standard data frame of the values that we found here. So now let's go back to where we stopped on the NaNs in those 4 columns. So I can choose, let's say, random values for R, random values for X, random values for C, and random values for I out of this standard data frame that I created. Would that be true? Maybe. But based on the data that we saw, we only saw that it's a combination of those numbers. So we did not see, for example, 0.08 with 0.5 for X, and let's say 5.7 for C, and then 10.4 for I. So we only saw unique set of data. So in order for us to do that, let's say more efficiently, we can either say, okay, it's based on this data frame, or the standard data frame that we created, we can only replace it by this or that. So replace the whole data, let's say the whole NaNs by one of them, it might be okay. Or maybe choose randomly. So we know how to do it. Let's say by one of them, just say, okay, all of the NaNs equals std.loc and then you say, okay, 3, for example. So you get this one. You can just simply and very easily change it. So R, X, and so on. So you get the value. But let's learn something new and let's do it with the random one. So let's do it like this. So I want to iterate over the NANs. And in each time, I choose a random number based on this standard data frame. So from 0 to 12. And this number would be a unique set of values that I will just simply replace. So let's say for I and so it's like this. So our data frame dot A would give me what exactly is NA and what it's not. Well, if I put this, but if I put it like this, it will basically give me the values where it's missing. So I need to iterate over those ones. So dot index. Now just print I. So those are the values that I want to change that are missing for R, for X, and so on. So if we just double check, is it always when R is missing, then X and C and I are missing? Let's do it here. So say df I and then R, then this is X, and this is for C. So see that it's always missing when one of them is missing. So all of them, all of the others are missing. So how can we do it? We need a random number here. So how can we do that random number? From NumPy, we already learned how to do it. So let's say num equals np dot random dot choice. And then here I just say, let's say 5, for example. This would always give me a random number below 5. So we need to do it below 13 or let's say below std.index because we know we have 13 indexes and then that's the number. So each time this will give me a new number, a new set of combination from our standard data frame. So now we have this number. How can we access, let's say, what's our number? That's 8. So std.log 8, that's my data frame. So now I want to say I is where I access it. So if I say df.log I and then r kilometer equals std.log and then this random number and then r. So this is the new value that needs to be in this data set. And because we want to be consistent, we don't want to create any new combinations in R or X or C. So we need to do it in the same for loop. So for R, X, C, and I. So X is here, C is here, I is here, and then say X, C, and then I. So now if we print this one and then try it out, let's see if we have our problem solved. So df dot is an A, and then any, basically we solved it. We do not have any NaNs more. So as I said before, it's only a matter of how you translate things or how you understand things or how you want to change it. It could have been much more easier, sorry, if you changed it simply by the mean. But in this case, you know that it does not make sense to have 3.2 cables. So there's nothing in reality like this. Or let's say for the voltage, even though there was no NANs, but we know that we only have 220 and 380 kVs in Germany in reality. So that's the same also for the R, X, C, and I, because these are, let's say, manufactured or manufacturers in standard. So there is nothing new. The last thing I wanted to show is this column here. So if we say, or if you show it, let's show the first one of it. So df.log, and then we say one. So I want to show the first one, just to show you what exactly it is. And if you remember the columns, we have one and two. So let's also show it. So df.log one with this column, or let's do them all together. So I want to show is that basically this one here means that the first node it's connected to is one, and the second is, so maybe one is not the best option. Let's say 50, just randomly. So 50 is connected between 0.52 and 0.56. So what does that exactly mean? Is that when you go to this SRID, so the standard reference ID, or the standard, say the decimal degree where exactly it's called, or exactly it's located, so the special reference system ID. So, and now we say, okay, log 55, this one. So it basically means that this is the first point. So we said the first point was, let's print it again, was 52. So 52 is located in 8.518, that's our longitude, and 53.20, that's our latitude. And then 56.2 is basically in 8.82, that's the longitude, and 53.10. So how can we exactly access them? Here you see it's a string. So if you check the type of this one, type here is basically a string. And if you want to access it, you need to split it. So if you say split by a comma, then you get two components here. So let's say we access the first one, that's our first one. And then we need to split it again just to get those numbers here. So to get the points of the first number. So let's do it like this. So what we need is this as, let's say, x, y, x, y. So x1, x2, y1, y2. So oh, longitude, latitude, 1 and 2. So if we split it by a comma, we may get this first comment here, or let's say this first element here, and this second element here. So the second element is quite straightforward, but it's difficult to get this one here. So if we try to split it without anything, so just split here. Now we get, this one is quite easy with a comma. So this one is element 1 is 0, or element 0 is this one. We can split it using the parenthesis here. Element 1 with a comma, and element 2 is already done. So let's say we want to define it. Let's say long 1 equals long 2 equals, so longitude and latitude, and then latitude 1 equals and lat 2 equals. So we said this one here is our longitude, so 8.5, which we got from this. How can I again split it? Is by saying split. Now we have it here. So this is the first one, we don't need it. This is the second one. So second is, so this is my first longitude. So here I want to say as a float with this one. So now it's 8.518. Let's say longitude 2 is, we need to go back to this one. So it's this one. This one is pretty straightforward by saying float. We need the last element of it. So from beginning till the last element. So this one here, now it's longitude 2. Now we need latitude, which if we go back here, it's So this one is not the longitude. This is the latitude of 0.3107. This is latitude 2. Longitude 2 is 8.82. This one here, which if you split it and then take the first one, then again split by a comma, and then take the second one. So it's done. Now latitude one is the same one as this one here, but instead of the first element, it's the second. Let's show it again. So we have 8.5. That's the longitude of 0.1, so long one, and 53.20, that's latitude one. And then we have 8.82, that's longitude two. And then 53.107, that's latitude two. So you need to try it out yourself, how to split it, in case you want to, let's say, calculate the actual distance, or to get the length that we get here is the actual length, but, or let's say the length that was reported, but you can calculate the actual distance if you have the degree or the decimal degree of those points, the longitude and the latitude. There's other options or other, let's say, applications when you have the GIS information. But as we said here, it's imported as a string. You cannot really do any mathematical operation on it or use it anywhere. So it's very important to prepare it before you start opening or let's say operating on it. And the last thing I wanted to say is that we have our standard data frame, and we need to learn how to export it, let's say as an Excel or as a CSV file. How to export it is like .c or to CSV, and then you say, okay, standard line types .csv. So this is for CSV, and this is for Excel. So this one would work, and this one would work. So now, where would they be exported? To the path that you have. Or if you don't have it here, or if it's not shown here, OS, then get CWD, so get current working directory. So if you go there, then you will see those outputs, so the standard line types as CSV and as an Excel file. With that, I finished today's video. Thank you for watching, and we see you in the next lecture.